Hi everyone, my name is Zhanhao Zhang and I'm a master's student in statistics at Columbia University. Today I'm going to give a presentation on my publication, An Efficient Geometric Search Algorithm of Pandemic Boundary Detection. This is a paper I wrote in collaboration with my co-author, Xifan Huang, who is currently a doctorate student at the University of Washington. So today's agenda of the presentation is as follows. First, I will go over some related works and the challenges we are currently facing. Then I will explain the problem setting by introducing the process of infection in our models. Next, I will illustrate the high-level strategies of our proposed non-geometric searching and geometric searching algorithm, along with their underlying conditions. I'll also discuss how we are adapting to the cases where people are not cooperating with the disease testings. After that, I'll give an asymptotic bound on the geometric searching algorithm, as well as the results from our experiment. Finally, I will close with the impact of our research on our society. And then I'll point out a variety of future research directions that can be led by building upon our works. Previous researchers have demonstrated that in order to reduce the peak of infection and mitigate the social economic impact of the pandemic, we should prioritize the testings of the individuals who have been in close contact with the confirmed cases. And we should also broaden the testings to the best amount of people in the population and enact quarantine policies in conjunction. Those strategies are all very consistent with our intuition. With the advancement of technologies, researchers are starting to investigate contact tracing approaches by leveraging high computing power. They keep track of the mobile proximity data to learn about the moving trajectories of each individual. Then they build a dynamic contact graph based on those trajectories, and then figure out who are at high risk of infection. To the best of our knowledge, we are the first to work on the pandemic boundary detection problems. While there have been a few inspiring research studies on the boundary detection in binary image processing, the common ways of boundary tracing we have gathered are either contour path following or traversing back and forth along the boundary in a sinusoidal path. The current approaches for learning the ongoing process of the pandemic in the population are very costly. The vast amount of disease testings in the population can introduce a very high burden on economics. The production of the testing kits, the recruitment and training of medical agents for conducting tests can cost a lot of money. And in the meantime, the vast amount of testing requires the compliance of a large fraction of the population, which can severely interfere with the normal life and work of people in the society. Digital contact tracing might sound a little bit more efficient than conducting a vast amount of testings because it leverages more computing power and much less human power. However, storing and processing the contact graph of the entire population can be very computationally burdensome, and the computational complexity can increase quadratically with the population size in the worst case scenario. In addition, as people are rapidly traveling, the digital contact tracing algorithm needs to keep running and updating very frequently in order to adapt to the dynamically evolving system. Before we dive into our solutions to those challenges, let me formulate the problem and explain how the infections are occurring. The disease infection process follows the SEIR framework. At the susceptible stage, agents have not been sick before and are susceptible to the infections. When the agents get the disease and turn into the exposed stage, the virus will first be in latency for a couple of days, during which the agents show no symptoms of the disease and are living a normal life. Those people can spread the disease to other susceptible people without awareness. After a few days, the agents begin to show symptoms and enter the infectious stage. They'll start the self-quarantine and therefore are no longer able to spread the disease to other people. In the final stage, the recovery stage, the agents are fully recovered with antibodies or died. In either case, they cannot be infected again, nor can they infect other people. First, we'll consider the case where only local infection is possible. We divide the world into an n by n grid. With a given population size, we allocate each person to the grid uniformly at random. Therefore, number of residents in the cell can be either 0 or positive. We start off with only one infected people on day 0. During the latency period of the disease, the patient 0 is able to spread the disease to other susceptible people. The patient can infect people within the same cell or people in the adjacent 8 cells. For each susceptible people in contact with the patient, he or she will get the disease with probability of P. Then a cell can be either an infected cell or a non-infected cell. If a cell is uninfected, then none of its residents have the disease. In contrast, if at least one of its residents has the disease, then we can say that the cell is an infected cell. If we look at the plot on the right-hand side, the blue cells are those infected cells, while the white ones are those all of whose residents have survived from the pandemic. It's also likely that some of the cells are uninfected because they have no residents. The cells colored in red are the uninfected boundary cells we are trying to identify. Those cells are uninfected themselves, but at least one of their 8 adjacent neighboring cells is infected. In the meantime, from each of the uninfected boundary cells, there exists a contiguous path to the border, such that it is not blocked by any infected cells or uninfected boundary cells. The red boundary connected by those uninfected boundary cells encloses the smallest region that contains all of the infected cells. Imposing social distancing and self-quarantine policies to all cells on or inside of the red boundary can prevent any disease transmission from the infected region to the cells outside of the boundary. It also minimizes the number of people who are forced to undertake the social distancing policy, while in fact, they have no way to spread or receive the virus. Therefore, it mitigates the social economic loss while ensuring the control of the disease transmission. It can be easily proved that the red boundary is a rectilinearly closed path, which is a very nice property that can be utilized by our geometric algorithm. In addition to the local infections, global infections are also likely because of the long distance travel of infected people. In order to stay consistent with Rayleigh's law of radial gravitation, we assume that the probability of the long distance traveling is discounted by the distance squared. And therefore, the long range infection probability is also inversely proportional to the square of the distance. Whenever there's a person spreading the disease outside of the cluster, the recipient of the disease will be the patient 0 of the new cluster, which will then start to spread the disease locally. The patient 0 will be revealed to us when they begin to show symptoms. The easiest and the most intuitive approach is the brute force searching that starts from patient 0, tracing and testing along the path of all infected people until all of the infected people have been tested. However, this requires the majority of the population inside of the boundary has to be tested. The non-geometric algorithm we propose can skip a large number of infected people. So starting from patient 0, we push forward in one direction and test all the cells along the way until we have found an uninfected boundary cell. Then we conduct a full search on all potential boundary cells. The potential boundary cells are uninfected cells adjacent to at least one infected cell, and all of those cells are connected. And finally, as we have identified all of the potential boundary cells, you can filter out the cells which are not on the outer boundary. In dense population with high disease transmission probability, the non-geometric algorithm does not test too many people more than the number of people on the outer boundary. However, when the population is relatively sparser and the disease transmission probability is smaller, there tends to have some holes of uninfected people, and that there will be quite a decent amount of potential boundary cells that are not on the outer boundary, and those will be tested, although they are not very required. So in order to further reduce the disease testing cost, we want to eliminate the testings on those cells that are not on the outer boundary. The intuition is that when we are searching and testing the neighbors, we want to prioritize the ones that is farthest away from the patient zero. So if the neighbor is indeed a potential boundary cell, then we'll move to that cell and keep testing its farthest neighbor. If the farthest neighbor is not a potential uninfected boundary cell, then among the remaining neighboring cells, we pick the one farthest away from the patient zero and then repeat the steps above. Building on the fact that the outer boundary is a closed path, we can repeat the process and keep testing the potential uninfected cells that are farthest away from patient zero counterclockwise when we have found a closed path, since we have always been tracing along the farthest potential boundary cells. All of the cells on the outer boundary have been covered, and most of the cells we have tested are also on the outer boundary. We can therefore terminate the searching. The implementation of the algorithm is also based on the regular linearity property of the outer boundary, which will be illustrated in the next slide. The position of the neighboring cell that is farthest away from patient zero depends on the location of the current cell, which is the compass direction of the current cell relative to the patient zero. For each cell, we test neighboring cells in the order of the ones on the right direction, the current direction, and the left direction. For example, if the current cell is to the north of the patient zero, then its farthest neighbor is to the east of the current cell. The notion of the right direction, the current direction, and the left direction for cells on each four sides of the compass is defined in the table on this slide. We take one of the simulation results as an example, and we use it to compare the performance between the geometric algorithm and the non-geometric algorithm. The red cells are non-infected cells. The blue cells are infected cells. The white cells are predicted uninfected boundary cells, and the black cells are the ones that are now tested by the searching algorithm. On the lower left of the plot, we can see that the full search algorithm has identified a lot of potential boundary cells that are inside of the outer boundary, and those cells tend to be scattered around the outer boundary. The plot on the lower right is showing the exploration of the geometric search algorithm, which can skip most of the cells that are not on the outer boundary and therefore skip most of the unnecessary disease testings. However, in both cases, the total number of tests conducted is much lower than the total number of infected cells, and both algorithms are able to enclose all infected people in the boundary circle. The reality is often harsher than the theoretical settings. Many people might refuse to get tested for the disease due to various reasons. If they are being non-cooperative, then we have no way to know about their infection status. We assume each resident may be non-cooperative with a given probability. Problems will arise from a significant number of non-cooperative people, as we'll have a sparser data. To resolve the issue, we merge each T by T square of cells into a supercell, and then we conduct the same algorithms on those supercells. In the case of non-cooperation, the predicted boundary is thicker for both algorithms because they are only testing with the granularity of the supercell. However, the full search algorithm is less likely to be distracted by the potentially uninfected cells that are inside of the outer boundary, because collapsing multiple cells into a supercell increases the number of residents of the cell, and therefore it is much harder to find a cell that is non-infected while also staying in the infected region. Both algorithms can still ensure that the predicted boundary can cover all infected people, which is a very desirable outcome, since we can still prevent the spreading of the disease when a fraction of population is being non-cooperative. Based on the theoretical results about the diameter of long-range percolation graphs, we have derived that for a population of size n with k-zone clusters of infected population, assume that the infection probability between two people is discounted by the distance squared, then the number of tests conducted by our proposed geometric search algorithm is in the order of O of k times log of n over log of n in order to find out the transmission boundary of the disease. It demonstrates that asymptotically, we are conducting much fewer tests than just testing every infected people. And in addition, the testing cost of our algorithm won't be penalized linearly with the increase in the population size. We have conducted a very extensive amount of simulation experiments to assess the performance of two algorithms under different settings. First, we have the infection probability for people in contact. It is from 0.05 to 0.2, incrementing by 1/8 at each step. The duration of pandemic is either 100 or 200, which represents the number of steps the whole system updates. In the case of non-cooperation, the supercell will be classified as an infected cell if the fraction of its residence is greater than 1/2 of the infection probability, or alternatively greater than 0. In the case of full cooperation, the thresholds will always be set to 0, which means that the cell is infected as long as there's at least one of its residents being infected. The probability of non-cooperation can take values from 0, 0.1, or 1/3. The population size is either 250,000 or a million, under the grid size of 500 by 500. Each cell has 1 or 4 residents on average, corresponding to the two population sizes. The experiment under each set of parameter settings will be repeated for 20 times to eliminate the effects from random noises. 3 performance metrics are evaluated to assess the efficiency of each algorithm. The test rates measures the number of tests conducted relative to the size of the outer boundary, plus the number of people within the boundary. The bottom line is that the test rate should be smaller than 1, so that the algorithm conducts fewer tests than the brute forcing. The second metric is misclassified as boundary, or MAB, which is the number of people predicted to be in the boundary itself, while in fact they are not. We want to reduce MAB so that we can reduce the number of tests conducted, and in the meantime, impose social distancing policies on fewer people who have no risk of spreading or getting the virus. And last but not least, the third metric, misclassified infected people, short for MIP, is a crucial metric for assessing the accuracy of the algorithms. It measures the number of infected people that are outside of the predicted boundary. We want it to be 0 all the time so that we can fully control the spread of the disease by simply imposing social distancing rules on people within the boundary. The effectiveness of our algorithm has been demonstrated by the promising experiment result. First of all, the MIP is 0 under all parameter settings, so we can cover 100% of the infected people using the predicted boundary. MAB and testing rates tend to improve with the increase in the infection probability and population size, with a decrease in the non-cooperation rate. In very rare occasions where the disease dies out very quickly, our proposed algorithm might not be advantageous, but this is totally not an issue because the total number of tests conducted will be very minimal in those scenarios. So the economic costs incurred are negligible. Geometric algorithm shows significant advantage over the non-geometric one when the infection is relatively sparser in the population, while both algorithms tend to perform equally well when the infection is dense or when we are dealing with non-cooperative cases. To the best of our knowledge, we are the first ones to bring up the notion of pandemic transmission boundary and work on the boundary detection algorithms. The current framework can be directly applied to the community-infecting diseases such as Ebola, as well as the spread of invasive plants, for example, the Japanese knotweed in Britain. It has the potential to reduce both economic costs and computational costs, while ensuring accuracy and efficiency in the context of non-cooperation. It's a pilot project for the pandemic boundary detection, so there are many interesting future works that can be built upon our work. First of all, we can tweak the definition of cells to be communities of an arbitrary number of people. So we can freely adjust the framework to adapt to the pandemic with different infection rates. For airborne diseases such as COVID-19, the infection rate will be relatively higher, where the grade of cells in household granularity might not be very applicable, as residents of those cells tend to travel among other cells quite frequently. In this case, a good approach is to increase the volume of the cell, so that most of its residents are only traveling within the same cell or to the adjacent cells. Therefore, we can investigate strategies to embed a map using a grid of cells. For example, on the Manhattan Island of New York City, we can map each one of its neighboring neighborhoods to a cell on the grid. One major challenge of this framework is the frequent long-distance travels among different neighbors, as people can frequently and easily travel to neighborhoods that are not adjacent to theirs by taking subways, buses, or cars. One potential approach is to abandon the use of geographical distance and adjust the distance measure to reflect the difficulty of getting to that location by driving a car or taking public transportation. And as the number of residents of the cell becomes larger, it's possible and not necessary to test every single individual in order to find out the infection status of the cell. Therefore, it might be interesting to explore potential group testing techniques used in combination of the random testing in order to get an estimate of the fraction of infected population of the cell accurately and efficiently. When we are testing multiple people in a batch, a positive result means that at least one of those people is infected. When estimating the risk of spreading disease from one cell to another, it will be very helpful to get an estimate on the proportion of its residents from one cell to another. Therefore, it could be worthwhile for future researchers to investigate the optimal number of people to test in a batch, considering the potential non-cooperation from those residents and any practical challenges of disease testing that might come up. And last but not least, the disease testing takes time, while the infection status is constantly evolving. Therefore, it's also important to make sure that the infection status of cell inferred from the disease testing results can still stay up to date with the infection status in the real time. Well, we can leverage group testing, random testing, or gateway testing to speed up the pandemic tracing progress. We can also enforce some social distancing rules in conjunction. One easy and intuitive way is to quarantine the individuals that are adjacent to the ones being tested. Alternatively, we can take economic costs coming from social distancing into account and reformulate the problem to minimize the impact on the latency from disease testing, subjecting to the constraint that the economic costs from the social distancing policies are below some threshold. A deep reinforcement learning on Markov decision process framework may be adopted. Finally, special thanks to my co-author, Dr. Qifan Huang, for his help with the problem formation, theoretical derivation, and proofreadings. We also greatly appreciate the guidance and inspirations from Professor Anna Cardin, Professor Amos Wyatt, Professor Stefano Leonardi, and Professor Elias Kousoupias at the early stage of the work. Those are the references. And thank you so much for your attention. I'm happy to take any questions.
Thank you for that wonderful presentation. And I'm seeing a few questions in the chat box from Sophia. She's asking effectiveness of contact tracing in emerging pandemics.
I'm sorry, could you repeat that?
Yeah, effectiveness of contact tracing in emerging pandemics. Let me just post the question here in the chat box for you.
Yeah,
you can just
that would be helpful.
Yeah. Yep, I have done that. You can just look at your chat box.
Okay. Effectiveness of contact tracing in emerging epidemics. Yeah, that's a very good question, actually. So that's also one of the reasons why I bring up one of the potential future directions. So while we are doing contact tracing and we are doing some disease testings, the lab tests can really take time. while we are waiting for the results, a lot of people are still spreading the disease outward. So we want to find some ways to keep track of, to stay update with the current disease status. So some approach is that while we are doing some contact tracing, we want to like at least imposing some social distancing rules on the populations that are not yet being tested or that are very likely to be around the boundary, so that we can make sure the boundary is not evolving faster than our testing.
Oh, okay, I could see the one more question.
Yeah.
I have sent it to your chat box and I'll just read it out. How effective are surveillance strategies for preventing epidemics on networks?
How effective are strategies for preventing epidemics on networks? What do you mean by the surveillance strategies? Can you like give a quick clarification on that? Are you talking about the social distancing?
Yeah, you can just take a random example and you can just explain it. No worries.
Yeah. So if you can, like, let me scroll back to some slides. Yeah, let me just actually take this plot as an example. So the reason why we are doing the pandemic tracing, the pandemic boundary tracing, is that we want to find a complex circle that can contain every single infected people. So suppose a people is spreading disease outward in a circular way, and then we just impose. Sorry about the noise. Okay, sorry about that. Let me quickly go through my example. So once we enclose every single infected people and imposing social distancing on those individuals, we can prevent them by spreading the disease either locally or through a long distance range. While in the meantime, we want now to impose social distancing rules on people who are not infected or who are not in close contact with potentially any infected people. So we want to allow those people to live a normal life and therefore reduce the economic loss. That is the main purpose of our study.
Oh, okay. Okay. Thank you. Thank you for being patient and answering all the questions.